Welcome to UVU CS3060 Lecture 9.6, where we talk about memory paging protection schemes. So memory protection is where we determine what pages are valid and what pages are invalid for a particular process. In most cases, a page table entry will actually have protection bits identifying if a frame is valid for read-write, or valid in general. We can also add a bit to indicate that the page is an execute only, meaning that the instructions that come from that particular frame can be executed by the CPU. Normally, each page table entry will have a valid bit. Valid-invalid bit will identify whether that actual page is loaded physically in memory and can be accessed by the process. Invalid means that the page is not in the process's logical address space. So as you can imagine, when a process first starts, pretty much all of its memory or its page table entries are marked invalid. As new allocations are made, those allocated pages will be marked valid so that the process can access them. We also use the page table length register to identify if a particular memory access is out of range of the page table. Any violation of these particular bits, whether it's valid or invalid, whether it's writing to a read-only page or attempting to execute when a page is not marked as execute, will result in a trap to the kernel, allowing the kernel to handle that process and potentially shut it down. This is actually where the term segmentation fault comes from. If you fault on a particular segment or page of memory, the operating system has been notified by the memory management unit that something went wrong. Either the page was invalid or you tried to access a page that wasn't allowed. So here we have a process's page, or process's logical memory with 6 pages, 0 through 5. We can see here that page 0 has a valid page and it references page number 2. This is true for 0 through 5. All of them are valid. You will note that page 5 actually has internal fragmentation. Even though there is an internal fragmentation, that entire page is accessible. So even if you access memory that's out of bound, sometimes it will be successful because of internal fragmentation. These pages, though, are going to be spread amongst the various frames of memory based on the frame number that's found in the page table. So each page table entry has a frame number as well as a valid bit to identify that as valid or invalid. Page number 6 is not part of the logical memory of this process, and page number 6 is marked invalid in this particular scheme. Any access to page 6 will cause the operating system to trap, and the operating system will likely kill the process that is attempting to access that invalid page. One of the very nice things about having a page table is we can actually share code and data between different processes. Sharing code is fairly simple because all we need to do is take the particular frame that is storing that executable and store it in the proper location for all the processes that are accessing that particular code. This is an interesting aspect of fork. When you perform the fork operation, you've been told that the process memory is copied from the parent process to the child process. Well, in a paged memory system, there is no actual copying of the memory space. All that necessarily has to happen is you just simply duplicate the page table. Each page table entry for the executable code can be copied directly into the child's page table. We can also do this with shared memory. If we use shared memory for interprocess communication, we can share pages between page tables, between process page tables. Thus, both processes have access to the exact same physical memory and can share between them. Of course, it is, we do have a point where we have private code and private data. So when a process doesn't share process, they'll keep separate copies of code and data. In the case of fork, while they may share the same process or same instructions, they don't necessarily share the same data. And that data will be differentiated with different frames. So while they may share code, they will have different frames for the same pages of data. That way, when the two processes write to the data, they will not overwrite each other. They will have private copies of that data based on the page table. So a page table, very interestingly, allows us a combination of both shared code and data and private code and data. Here's an example. We have three processes here: process 1, process 2, and process 3. Now, all the processes share the same first 3 pages. Notice that the page table for process 1 has 3, 4, and 6 in the first 3 page table entries. 3, 4, and 6 for process 2, and 3, 4, and 6 for process 3. This is the actual executable that is shared between each process. Very frequently, this is also read-only areas or execute-only areas. So we have that shared, but each process will have its own unique data area. Data and stack are usually maintained in their own page table entries. So we see process 1 has its data in frame 1. Process 2 has its data in frame 7. And process 3 has its data in frame 2. This brings us to the end of lecture 9.6, where we talk about memory paging protection.